Hello everyone, we're back. So my internet was down earlier. Well, when I say earlier, it's actually what, like 5 hours ago, 4 or 5 hours ago. So internet was down, and yeah, I watched the previous live stream and I realized that a lot of the content was actually not recorded. So let me recap what happened. First of all, we had a first solution, which is recursion, and it did not. It was correct, but it timed out, right? It timed out. Now it's trying to figure out why did it time out. Is it like was it because the algorithm was wrong, like the time complexity or whatnot? But what I feel is the time complexity is indeed still OMN. However, I timed out and I took a look. Like I passed all the test cases. It's just so the algorithm was just a hair of too slow. So my guess was, the recursion and everything just to make it slow. Oh, hold a sec. I just realized I have a print. Maybe that was the reason why it got rejected. Oh, hold on. That might be the reason because I have a print. Anyway, I'm gonna try this one again. I want to see if I have a print in the submitted version. But anyway, this one got timed out, and I don't know why. Feel like it's ON. Why would it time out? So I use a new solution, which is basically I think it's the same as this one, but this one's bottom up. Now since it's bottom up, it doesn't require any recursion, and I also do it in place, so it doesn't require any space, right? And I just submit it, and then it passed, right? It passed. I passed with pretty good result, right? Everything accepted. 72 milliseconds. Actually, I'm gonna check this one more time, so we can see. Oh no, there's no print. Yeah, you see that? 45 tests passed. So all the test cases passed, but it took too long. So it was good, but it took too long. They might have changed this as well. But anyway, it took too long, and my guess is just because the DFS will usually take longer, and also because of this, I have to create a new stuff. I have to create a new, basically a DP table. So instead of doing that, I do a bottom up, and apparently bottom up was good. Let's take a look. Well, we hit the majority. The bottom up was good. So the method, let me explain this method in detail. I mean, it's just bottom up, so it's the same concept, right? So let's go back to Dungeon Game. All right. So yeah, we got into this. So the idea is this position, right, is certain, is static, right, deterministic. So we can know this position. And this position is deterministic as well. We're talking about the minimum HP, minimum health required to reach this is 1, right? It's deterministic. And the minimum to reach here, because this is 1, and this one goes here, so the minimum to reach here is also deterministic, right? The minimum. Yeah, because well, from here to here, right? Because this one can only be accessed from these two, right? So if the minimum required to reach here, I mean, after reaching here, right, we'll get 1. Health is 1. So that's the afterwards. So before we reach in this, it's about to enter the cell. The health must be 6, right? So that will be the health after finishing this cell or after finishing this cell. And because these two are the only cells that can lead to this. So the minimum health entering this cell and entering this cell is also deterministic. So the minimum health entering this cell must be 5, right? Because the exit health is 6, so the entering health is 5. And here the exit health is 6, so the entering health must be, well, because it's 30, so the entering health is 1. Because we don't have to, because it's just adding, so 1 will be sufficient. So we have this, we have this. Similarly, we can have this, and we can have this, right? So the rightmost column and the bottommost row, everything can be deterministic. Now, once we do that, we just shift our focus to this point, to this cell, right? So this cell, the entering health for this cell is deterministic because we know the minimum entering health for this and this. So the minimum entering health for this is 6. Oh no, for this is 5. My bad. So it's 5. Minimum entering health for this is 1. So we know the minimum entering health for this is either 15 if we go this way, or 11 we'll go this way. We take the smaller of the two. So the minimum entering health for this is 11. And this one is deterministic because we know the minimum entering this is 11, and the minimum entering this, which is 2. Right? Minimum entering this is 2. So we can figure out minimum entering here will be, so 11, 2, so it will be 5. So minimum entering this will be 5. So similarly, we know the minimum entering health for this. I'm not going to calculate it, but we know this. Now these two. Now when they're all done, we're looking at the first one. It's deterministic, right? So by doing this, calculating the minimum entering health for each cell, we're going to go from bottom up. So from lower right, we're going to populate back up to the top left, we will be able to get. So that's exactly what this algorithm is. So I start by doing this. You can see this is the rightmost column, right? And then we just take the we first set the lower right corner, right? Lower right corner once we set, and then we set the rightmost column, bottom row. Once they set, we have I and J, and then they just going to do, every time we're going to do just a column and a row. Once we're done, we move like diagonally up a column and a row until we cannot go anymore. And then we return the star. So that's basically what it is. Okay, so now let's just write. This is a bottom-up DP solution, similar to solution 1. We start from the lower right corner. It's we know the the min exit health for this cell is 1. So we can compute the min entry health for this cell, which is this thing, right? Which is this thing. It means if the cell has a negative number, we do 1 minus, right, that negative number. If it is a positive number, right, smaller than 1, then we do 1 minus that number as well. However, if the positive number is bigger than 1, that means the minimum entry health can be just 1, right? Because we're going to boost all that up, so it doesn't really matter. Now this logic will be used to compute all the entry health for all the other cells. Then we can compute the entry health for the rightmost column and the bottom row. Once that is done, mean entry health, right? When that is done, we can shift shift one layer inward to compute the min entry health of the of row n minus 2 and column n minus 2. We continue doing so until we reach position, right? Position 0, 0, and compute the mean entry health of the start. All right, so that's it. The runtime is OMN, right? Where M is the number of rows and N columns. And we hit a pretty good result, which is 72. So we hit 72 milliseconds, or 80% ranking. I don't know, I still feel this one timeout is a bit weird. But anyway, bottom up is fine. So we're gonna go, I don't think we can see this. Let's see the discuss. Binary search and DP, interesting. Binary search, DP. Minimum value is 1, maximum value is this. So mid is this. If is good mid. Then answer is mid. Has initial health point. Can get. Can reach from cell to cell. I don't quite understand. Is good. So we need to find the is good mid. Like if it's good, answered on mid, and then right equals mid minus 1, minimize health. Else increase initial health. To check is good, as an initial health point, let DP denote the maximum health we can get, and we can reach from cell to cell. The maximum health we can get when we reach this. If we find a path, which this means the knight can survive successfully. So we have the starting point, and then if r larger than 0, why would r not be larger than 0? Oh, r could be 0. Well, what if r is 0? Oh, we go different directions. So we're gonna max this, max myself. Now max this compared to the previous cell and the grid. So it's a similar idea. Okay. So the bottom up. Need, DP need, okay. Oh, we create a little bit longer. We create a little bit larger. I see what you did there. We just create a little bit larger. So we can avoid all this hassle. So it's the same, right? It's the same as mine, but it's much easier. But let's say, how did they walk? They walk column first, right? Okay, and then we do minimum dp. Hold on. R plus 1 row, next row, and then okay, so we do these two, and the minimum of this minus a grid, okay, and then we say if need is smaller than 0, we do 1, otherwise it's going to be need. Alright, so we can populate the entire row, bottom row, then what? Then we go up. Yeah, I think this might work. Alright, bottom row we can do, and then yeah, we don't have to do it this way. We do bottom row, and then we can do the second to bottom row, because this one is yep. That's much cleaner. That's much cleaner than mine, but it's the same idea, right? It's the same idea, but it's much cleaner. Let's write it this way, right? Let's write it this way. So I'm gonna credit him, but also note that this is it's the same idea. So def blah blah blah. Oh, shoot. Then we're gonna say this one. But we do have to create a new DP table, right? So solution 3. This is from the discussion linked below. It's the same, right? It's the same solution as solution 2, but with much less clutter in the implementation. So we create a new DP table. Wow, wonderful. Create a new DP table. So we just call it DP, right? And we make it slightly bigger. Math.inf, right? Math.inf times n plus 1, right? For this in range m plus 1. So it's slightly bigger, so we can combine the logic for these two. And we have to do DP. We have to do this, right? So basically we say we're going to go one more layer here. No. And everybody going to be infinity, but for this cell, this and this has to be 1, right? Or these two has to be 1. So this is going to be row m, right? And a column going to be n minus 1 equals dp. Row n minus 1. No, row m minus 1, right? Column is n. So what we're talking about is m is this row. N minus 1 is this position. Or m minus 1 row is here, n is here. So these has to be 1, right? And then we don't have to do the this one and this one. We can just go row by row, going this way. Because once this row is done, this one can be done, right? This one, because we have this, and once this one is done, this one can be done. So it is possible just to go for I in range, right? M minus 1, minus 1, minus 1, right? And then for j in range, n minus 1, minus 1, minus 1, right? And then we can just say dp ij will equal to max min dp I plus 1 j and dp I j plus 1, right? And min of this minus dungeon ij and 1. So it's the same as this, minimum minus dungeon and then 1, right? And then once we're done, dp return dp 0, 0. Wow, look at this. What happened? Wait, why are you complaining? Huh? What is this? Expected an indented block. But not indented enough? Oh! I forgot. I didn't indent it. Oh, there you go. Nice. So this is better in terms of the coding part, right? The coding part is better. Let's see. Yep, the coding part is better. So I like this one. I like this one better. I mean, overall, not actually too difficult, right? It's not too difficult. It's okay. It's okay. Well, we do have to do bottom up. I think they specifically not let. I mean, it could be other reasons, but I feel like they specifically not let the top-down DP solution to work. I don't know. I'm just guessing. All right, this is part 2, and we're good. We're good to go. I'll see you guys tomorrow. Adios.